In the last few lectures, we have been discussing diffusion, first mass diffusion and then thermal diffusion in two types of fluids, liquids and gases. In gases, mass and thermal diffusion are due to physical transport of molecules across a surface. Across the surface, when there is a variation in the density of a quantity, mass density for mass diffusion, energy density for thermal diffusion. When there is a variation in the density of a quantity across a surface, there is a net flux, because molecules going upwards go from a distance approximately 1 or of the order of 1 mean free path below the surface. Molecules coming downwards come from a distance of the order of a mean free path above the surface, and the concentrations are different at those two locations. If you recall, in both of these cases, the diffusion coefficients are equal to products of the mean free path and the molecular diameter. Okay. In both of these cases, they are equal to products of the mean free path and the molecular diameter in gases. These are obtained by writing expressions for the flux going upwards, the flux going downwards, and taking the difference between those two and expanding out the densities of the quantities in a Taylor series about the value at the surface itself. Okay. We get a first order correction whose magnitude scales as the mean free path divided by the macroscopic length scale. And because of that, the diffusion coefficients turn out to be of the order of the mean free path times the RMS velocity. We had got estimates for the mean free path and the RMS velocity in gases. Hydrogen, for example, was approximately 2000 meters per second. The RMS velocity, nitrogen and oxygen were of the order of 500, and the mean free path from the distance it takes for a molecule to travel before it collides with a second molecule. And that distance was inversely proportional to the number density of molecules and the diameter of the molecules. Okay. And this was in the range of 10 power minus 7 to 10 power minus 8 meters, or 0.1 microns to 0.05 microns roughly was the range. Okay. And based upon that, we had got the diffusion coefficients as approximately 10 power minus 5 meters per second for mass in a gas. This is the same magnitude for the thermal diffusion also in the gas, because the mechanism is the same. I had given you some more numerically accurate expressions for the diffusion coefficients in a gas. Okay. In liquids, we had also calculated the thermal diffusivity in a gas, okay, using the exact same principle. Energy from a distance of the order of a mean free path below going upwards, energy from a distance of the order of a mean free path from above going downwards, the difference between the fluxes going up minus going down, and use a Taylor series expansion. In this case, the RMS velocity and the enthalpy density are both functions of position. Okay. And therefore, you have to take the derivative with respect to position of both of these, okay, and subtract it out. But in the end, you get a diffusivity that is proportional to the mean free path times the root mean square velocity. The thermal conductivity is rho Cp times that diffusivity. Okay. Thermal conductivity is rho Cp times that diffusivity. We had derived all of these in the previous lectures. I had given you a more exact expression for the thermal conductivity, and we had actually done a calculation, okay, of the diffusivity, thermal diffusivity in air, and based upon this we had got reasonably accurate results, okay, based upon the molecular diameter, the mean free path, and so on. We have also looked at mass diffusion in liquids. Okay. There, if you recall, I had said that the mass diffusion in liquid is lower than what you would expect. Okay. The reason is because for a liquid molecule to move in any one particular direction, right, it has to displace, okay, surrounding molecules, okay, because the liquid is very densely packed and all the molecules are very close to each other. If you want one molecule to move in any direction, surrounding molecules have to execute a cooperative motion. So, that space is created for this particular molecule to move in one particular direction. And this cooperative motion is a very rare event, and because of this the diffusion coefficient is lower than what you would expect based upon the mean free path and the molecular diameter. Okay. And the estimates that I had given you were 10 power minus 9 meter square per second for small molecules, down to 10 power minus 13 meter square per second for large molecules. And we had also discussed the calculation of the Brownian diffusivity using the Stokes-Einstein relation. Now, what about thermal diffusion in liquids? Okay. The diffusivity in liquids is not the same as the diffusivity in the mass diffusivity in liquids, because the mechanism of thermal diffusion could depend on the type of liquid. Okay. In mass diffusion, a molecule has to necessarily physically move in order to mass to be transported. In a liquid, a molecule does not have to physically move for energy to be transported, because molecules are all densely packed. Okay. Because molecules in a liquid are densely packed, okay, you do not require a physical motion of a molecule for transport of energy. Energy could be transported due to various mechanisms, including intermolecular forces. So, because you do not require molecules to physically move, the diffusion coefficient in a liquid for energy could be significantly higher than that for mass. Okay. Because for mass, a molecule has to physically move. For energy diffusion, a molecule does not have to physically move. Okay. So, the transport could be due to various factors. Okay. So, for example, in liquid metals, you have molecules with a delocalized electron cloud around the molecules. Okay. The delocalized electron cloud around the molecules, and because of this, energy could be transported through the electron cloud itself. You do not require molecules to physically move. Okay. Energy could be transported due to the electron cloud itself, and because of that, thermal diffusion is a very fast process. Okay. So, for example, for liquid metals, okay, thermal diffusion through the electron cloud, okay, which means that the ratio Prandtl number, which is equal to nu by alpha, because thermal diffusion is very fast, this turns out to be much less than 1. Okay. For example, for liquid mercury, okay, the Prandtl number is equal to 0.015, which means that thermal diffusion is approximately 60 times faster than mass diffusion. Okay. So, it depends upon the mechanism of diffusion. The mechanism of diffusion matters in the case of thermal diffusion. In this case, in the case of liquid metals, the thermal diffusion is much faster. In the case of organic liquids, where you do not have easy transport of energy, okay, thermal diffusion smaller than momentum diffusion. The Prandtl number will be much larger than 1. Okay. Okay. If thermal diffusion is much smaller, then the Prandtl number is much larger than 1, and it could vary in the range 10 power 2 to 10 power 4, okay, depending upon the liquid. Okay. In this case, the thermal diffusion transmission of energy is much slower, transmission of thermal energy is much slower, okay, than transmission of momentum. Okay. So, you could have a range of Prandtl numbers, ratio of momentum to thermal diffusion. In the case of liquid metals, conduction is very fast, it is through the electron cloud, and therefore, the Prandtl number is very small. Case of organic liquids, Prandtl number is large, and for water, okay, Prandtl number is order 1. Okay. Water, so therefore, there is a range of diffusion coefficients in liquids depending upon the mechanism of diffusion. In metals, it is due to the electron clouds, and therefore, it is a very fast process. Thermal diffusivity is very large, of the order of 100 times the momentum diffusion. In the case of organic liquids, thermal diffusion is a slow process, okay, and water is somewhere in between. Okay. So, in liquids, the ratio depends upon the mechanism of energy transport. And the details of the transport matter, these details is out of the scope of the present course, because we have not dealt with intermolecular interactions in great detail. But however, this Prandtl number for constant for many typical liquids will be available in standard tables. Okay. Finally, we discuss momentum diffusion. So, the picture is very similar. I have a surface across which all molecules are getting transported. In gases, okay, in which now, okay, this is z is equal to z naught. The velocity in the x direction, okay, is a function of z. Okay. So, to put a coordinate system here, x is along the flow direction and z is perpendicular to the flow direction in the direction of momentum transfer. Okay. And what we would like to do is to estimate the shear stress or the rate of or the momentum flux across the surface. So, what is the momentum that is being there is a net momentum flux, because molecules that are going downwards are going from a distance approximately or of the order of 1 mean free path above the surface, where the mean velocity is higher. Molecules that are going upwards are going at a distance approximately 1 mean free path below the surface, where the mean velocity is lower, and because of this you are having a net transport of momentum. Okay. The flux of momentum downwards through the surface. Okay. Okay, is going to be equal to the velocity, the momentum density at that point, okay, times the RMS velocity. Okay. So, I can write this as AM times VRMS. AM times VRMS is the average velocity downwards through the surface. Okay. VRMS is the root mean square fluctuating velocity, that is in all directions. The contribution perpendicular to the surface will be some factor times that, okay, times the momentum density at the location z plus b lambda. Okay. The momentum density at that location is equal to the number density, the molecular mass times Vx at z naught plus b lambda. So, this is equal to the the velocity estimate of the velocity perpendicular to the surface, and this is the momentum at a location z naught plus b lambda. Okay, that is thus, okay, that is the momentum flux downwards. Okay, so let me call this as momentum flux here. The momentum flux upwards is similar, except that it is coming from a location below the surface. The shear stress in this case is defined as the momentum flux downward minus the momentum flux upward. Okay. The shear stress is equal to momentum flux downwards minus momentum flux upwards. Okay. Why is that? Okay. So, typically when we dealt with mass and energy transport, okay, the flux was defined as qz as positive if it is in the plus z direction. Okay. Energy was defined as positive if it is in the plus z direction. Therefore, a positive flux increased the energy in the volume above the surface. Okay. Similarly, for mass transport. Okay. Similarly, for mass transport, okay, the z was defined as positive, okay, if it increased the mass in the volume above the surface, if the flux was in the plus z direction. That was the convention that we used for deriving Fick's law for mass diffusion and Fourier's law for heat conduction. Okay. The convention used for momentum transfer is the opposite. Tau xz is equal to force per area in x direction at surface with outward unit normal in z direction. Okay. Force per unit area in the x direction at a surface with outward unit normal in the z direction, that is, the unit normal to the surface is in the plus z direction. The outward unit normal, okay, so you are talking about the force exerted on the volume below, okay, because the outward unit normal is in the plus z direction, force is exerted on the volume below. It therefore, it increases the momentum of the volume below. Okay. If tau xz is positive, it increases the momentum of the volume below. Okay. Now, the momentum of the volume below will be increased if you take the momentum flux downward minus the momentum flux upward. Okay. So, that is the opposite of the convention. So, the shear stress, if you relate it to the mass and energy fluxes, the shear stress actually increases the momentum of the volume below. So, it is the downward, okay, flux at the surface opposite to the outward unit normal. Okay. That is why you take the momentum flux below minus the momentum flux going upward. Okay. So, this will be equal to Am Vrms into Nm into Vx at z plus b lambda minus Vx at z minus b lambda. Note that Vx I am using here for the flow velocity, not for the molecular velocity. Vrms is the molecular velocity and Vx is the flow velocity. Okay. So, I am using the expression Vx here for the average flow velocity, which we had defined earlier. Okay. It is you take the molecules at a location, sum up all the momenta of the molecules, divide by the mass, you get the flow velocity. And if I once again use a Taylor series expansion, I will get this as Am Vrms Nm into Vx at, this should be z naught So, this is the expression for the shear stress, and when I use a Taylor series expansion for the velocity, and once again these two cancel out, and I get A m Vrms n m b lambda dvx by dz with a factor of 2 here. This is the same expression as Newton's law for viscosity. Note that we had said earlier Newton's law for viscosity there is no negative sign because it is the force exerted on the volume below. This coefficient here is the coefficient of viscosity. So, if I write this as mu dvx by dz, I get the coefficient of viscosity. Mu is equal to 2 A m b n n m Vrms lambda. That is the viscosity coefficient to within some order 1 dimensionless factors A m and b. This product, number of molecules times the mass of a molecule, is just the mass n is the number of molecules per unit volume, m is the mass of a molecule. The product of these two is just the density of the gas. Okay. So, therefore, this can also be written as 2 A m b rho Vrms lambda. Okay. This is the viscosity. Kinematic viscosity is equal to mu by rho, momentum diffusivity, which is 2 A m b lambda Vrms. Okay. This has the exact same dependence on the mean free path and the molecular diffusivity, the molecular fluctuating velocity as the mass diffusivity and the thermal diffusivity. They all have the same dependence. Okay. And that is not surprising, the dependence is the same because the mechanism is the same. In a gas, whether it is diffusion of mass, momentum or energy, diffusion takes place by physical transport of molecules across the surface. Therefore, the thermal diffusivity, the mass diffusivity and the momentum diffusivity all have the same dependence on the mean free path and the molecular diameter up to a multiplicative constant. Okay, up to a multiplicative constant. As in the case of thermal diffusion and mass diffusion, you can get a more quantitative estimate from kinetic theory of gases. That estimate turns out to be 5 by 16 dm square, okay, root of m kb t by pi. Okay. And nu is equal to mu by the mass density, which is mass times the number density. Okay. So, this is equal to 5 by 16 n dm square root of kb t by pi m. Okay. So, note that this 1 over n dm square is proportional to the mean free path. You recall that lambda was equal to 1 by root 2 pi n dm square. Okay, that is proportional to 1 over the mean free path, and this whole thing is proportional to Vrms. Okay. Vrms is equal to square root of 3 kb t by m. Okay. So, therefore, the diffusion coefficient is once again proportional to the mean free path times the RMS fluctuating velocity. And both of the viscosity note is independent of the number density. or the density of the gas. Okay. It depends only on temperature to the half power, okay, in for hard sphere molecules. The diffusivity goes as 1 over the density. Okay. So, in gases the viscosity is independent of density. Okay. It depends only on temperature. Okay. It is proportional to square root of temperature for hard sphere gases. As I said, there can be a slight variation in the temperature dependence if you take into account the intermolecular interaction as consisting of attractive and repulsive parts. Okay. So, this is as far as thermal diffusion in gases, momentum diffusion in gases is concerned. We have calculated expressions for the viscosity and the momentum diffusivity. Okay. Momentum diffusion in liquids. Molecules are all densely packed in a liquid. However, if I impose a velocity variation, okay, momentum transport of the, in this case, the x momentum in the z direction. Okay. The momentum transport of x momentum in the z direction does not require physical motion of molecules. Momentum can be transported due to intermolecular interactions. In the case of hard sphere, this will be discrete collisions between liquids. So, if I have a surface in a liquid, I do not require a molecule to physically move to transport momentum. It is sufficient if a molecule on one side of the surface exerts a force on a molecule on the other side of the surface. That is sufficient to transport momentum through the liquid. Okay. So, transport of momentum through the liquid does not require physical motion of molecules. It can be transmitted due to intermolecular interactions. Because of this, momentum transport is a much faster process than mass transport. Mass transport actually requires a molecule to physically cross the surface for mass to be transported, and because of that you require cooperative motion of surrounding molecules. Momentum transport does not require a molecule to physically move. It is sufficient for a molecule on one side of the surface to exert a force on the molecule on the other side of the surface. Therefore, momentum transport is a very fast process in liquids. And because of this, the kinematic viscosity in water, for example, okay, if you take water for example, nu is equal to, the viscosity is about 10 power minus 3 kg per meter per second divided by the density, which is 10 power 3 kg per meter cube. Okay, this is equal to the viscosity divided by the density. This is approximately 10 power minus 6 meter square per second. Okay. Recall we had said for small molecules the diffusion coefficient is 10 power minus 9 meter square per second in liquids, okay, which implies that the Schmidt number is equal to nu by d, which is equal to 10 power 3. Okay. Because momentum diffusion is much faster than mass diffusion, the Schmidt number, the ratio of diffusivity is large, okay, and therefore, we consider therefore, momentum diffusion in a liquid, okay, is a relatively fast process compared to mass diffusion. If you recall, we had considered the limit of high Peclet number laminar flows, and we said that that is possible only if the Schmidt number is large. You can have high Peclet number where convection is dominant as far as mass transfer is concerned, and low Reynolds number where diffusion is dominant for momentum transport, only the Schmidt number is large. In liquids actually that is actually true. Okay. The Schmidt number is large in liquids because momentum diffusion by intermolecular forces is much faster than mass diffusion due to the physical transport of molecules. The ratio of momentum and thermal diffusion depends upon the mechanism, as we had discussed in the last lecture. In liquid metals, for example, thermal diffusion is very fast. Therefore, the ratio of momentum and thermal diffusion, the Prandtl number is small. Organic liquids, momentum transported faster than energy, and therefore the Schmidt number is the Prandtl number is actually large. So, this is a brief summary of the mechanisms and estimations of the diffusion coefficient. In liquids, we could get good estimate, I am sorry, in gases, because the molecular picture was simple, transport occurred only due to the physical motion of molecules across a surface. We could get quantitative estimates for mass, momentum and energy diffusion. The diffusivities are all of the same magnitude, all proportional to the mean free path times the RMS velocity. In the case of liquids, it depends on mechanism. Mass transport depends on physical motion of molecules, it is very slow. Momentum transport can be done by molecules on one side of a surface exerting forces on molecules of the other side of a surface. That is a relatively fast process. Thermal diffusion in liquids depends upon mechanism. In liquid metals, for example, it is very fast. In liquids like organic liquids, it is relatively slow. So, this is a summary of the diffusion processes. Next lecture, I will start dispersion. I will see you then.